So the dot product. I do know that American students have a weird habit from school sometimes to write down 4 times 7 with the x. Don't do that. Now we're going to cover dot product and cross product, and they mean different things. 4 times 7 and 4 cross 7 mean the same thing in terms of numbers, but not the same thing in terms of vectors. Those will be 2 different products. One called cross product, the other one called dot product, just from visual representation. We're going to start with the easy one, which is a dot product. It has a dot. The dot product looks like this. Let's write down. If A vector is A1, A2, A3, remember in the notation, pointy brackets, and B, B1, B2, B3, then the dot product multiplies corresponding components, A1 and 2, A3, B1, B2, B3, called components. So I'm multiplying A1, B1, A2, B2, A3, B3, and add the results together. So that is, let's put it in a box, the definition of a dot. Wow, that's a fat box. That's a definition of a dot product. Here it is. The dot product, the most important difference with cross product, and there are other products, by the way, is that the dot product will be a number. The result will be a number, while the cross product will give you a vector. Dot product gives you a number. We're going to call this scalar number. Because A1 times B1 is a number, and then you add to another number, it gives you a number. So that's important. Dot. See this? I made it fat. Dot. Let's see 2 more formulas. With this dot product, it will be easy to do 2 things. To find the angle between vectors. Not as theta, but as cosine theta, but whatever. Let's write down, if theta is the angle between A and B, then dot product gives you absolute value of A times absolute value of B times cosine. What does this absolute value of A and absolute value of B means? Do you remember? Vector length, magnitude. Those are synonyms. Vector length, magnitude, size of the vector. So remember, I like the double one more. But you can use any double or one. Wikipedia says both are fine. That's a magnitude. Magnitude. And we just learned the formula for that. The square root, component square plus component square plus component square. So this is how we can find the angle between vectors. Cosine of theta. We'll have this cool formula. You'll see it everywhere in the book. So we can derive it. Cosine theta. Remember, circle with the wiggly thing inside is theta. Cosine theta is A times B over A times B. The difference is only the numerator is a dot product of 2 vectors. The denominator is a product of lengths of those vectors. Since the numerator gives you a number and denominator gives you a number, cosine of theta is also a number, which makes sense. To be weird if cosine of theta is a vector. Angle is the angle. So this is the formula you will see everywhere. Visually easy to remember. A times B over A times B. Dot product over lengths product. And then the last thing is how to know if A and B are orthogonal, which are perpendicular, right? Perpendicular. If the dot product gives you 0, if and only if. Very nice American notation, actually, my favorite American notation. If and only if, IFF. You will see it a lot in upper level math classes. I like it a lot. It's not international notation, but it's fun. If and only if. That means it goes both ways. If dot product A times B is 0, then vectors are orthogonal, and the other way around. If vectors are orthogonal, then the dot product better be 0. That's the idea. So A times B is 0. Dot product, make sure you put dot. Interestingly, when I was teaching this calculus 3 class for the first time in the United States, I realized that I don't remember the name dot product and cross product in my language. I don't remember this title. So I got confused and I checked Wikipedia and then translated it to my language. Yes, we don't call them this way. Actually, the way we call it is better. We call it scalar product because the answer is number. And vector and cross product is called vector product because the answer is a vector. I told students they actually like it more last time. So in Wikipedia, you will see some countries called scalar product, because the answer is a scalar. So here it is, the idea. The dot product of two vectors give us a scalar or number. The other names of dot product is a scalar product. In upper level classes, you will find inner product. Inner product because of the formula. How do I calculate inner product? Multiplying inner parts of each vector. That's components. So it kind of goes inside of the vector, multiplies them out, and adds together. The formula is this again. AB plus AB plus AB, basically. But all of those are three different components. Let's do the example, and I will tell you something pretty fascinating about this. These two homeworks were very technical. We will ask you to calculate lots of things. In general, when we introduce vectors at the beginning, it becomes very technical. Find the sum, find the dot product, find the cross product, divide, subtract. And then we're going to go to applications. And applications are pretty amazing. But to go to applications, you need to know some basic operations. So we learned how to add vectors and subtract them last time. Multiply by a number, which is shrinking or stretching. Creating a unit vector, which is shrinking to vector size 1. Now we're learning how to multiply them. And apparently there are two ways to find a product of the two vectors. And the first one is a dot product. Move on to example. Let me know if it's too fast. Example. If A is 1, 2, 3 and B is 4, 5, 6, let's find dot product A times B. See, I put dot. So not cross, not nothing. It should be dot. A dot product. Let me show you the notation, which you don't have to write down in the future, but the first time it's nice to know this. Notation is 1, 2, 3, that's A, dot product, multiplied by 4, 5, 6, that's B. What you do, you multiply component by component. So now that's the formula. 1 times 4 plus 2 times 5 plus 3 times 6. See, no vector notation anymore. The answer should be a number. Scalar. Scalar means a number. And the answer is 32. Yay! The dot product of two vectors is a number 32. That is the idea. Kind of, you see, that's very technical and not more than that. Make sense? So last time, actually, you mentioned A times A, remember? There was A times A comment. A times A, whatever we would call A square with numbers, what is going to be with vectors? A times itself will give you a magnitude. Let's check that. So calculate A times A. Okay, so A times A dot product will be 1, 2, 3, if A is still 1, 2, 3, times 1, 2, 3. That gives you 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. That is 14. Okay, interesting. So A times itself gives you this number. But if I find the magnitude, which we learned from last time, the length of the vector, the length, double absolute value, or just absolute value, but I like double. The square root of square each is going to be 1 squared plus 2 squared plus 3 squared. That is square root of 14. And that is a correlation between a dot product and a magnitude. A times A gives you a magnitude squared. So you see the only difference is a square root. So if I square, this is basically the formula. If I square magnitude, I will get a dot product of A by itself. A times A. Dot or scalar product. Bless you. See, there's a very not funny old Soviet joke about that. If someone sneezes, that means the person who was talking right before that is telling the truth. Very, so not funny, but somehow like my students knows. If someone sneezes, see, I did not mess up. Just for you to know, which you should pay attention, because sometimes I'll make mistakes always on purpose to make sure that your notes are good. A times A equals A squared, size of A squared. So it makes sense A squared from a number point of view. 2 times 2 is 4. But from a vector, remember, vector is not a number. Vector is a line that has direction and the size. So it's more complicated than that. Okay, one more example. What if we ask you to check if 2 vectors are perpendicular? Do you know how to say perpendicular in Russian? Perpendicularny. Almost the same. Perpendicular, perpendicularny. But you see I'm saying grrr, because that's how you should say it, by the way. Perpendicularny. So, if I ask you to check if 2 vectors are perpendicular, up until final exam, that will be like one of the multiple choice questions, to be honest. There's one way to do it, graph it, or the easy one, you find dot product. Find A times B. Why? Because it must be 0 if they are perpendicular. 0 not vector. So we have 0 vector, 0 number. 0 in this case, it's a number, a scalar. Okay, so I'm calculating A times B. I'm not going to even rewrite them anymore. 1, 2, 7, 3, 2, minus 1. Just quickly multiply. Let me wait for you. Check if it's 0 or not. A times B. Is it 0 or not? Yay. Let's check. 1 times 3. So I'm multiplying corresponding components. Times 2 times 2. Plus 2 times 2. Plus 7 times minus 1. 7 times minus 1. Adding together gives me 3 plus 6 minus 7. No, 3 plus 4 minus 7. 3 plus 4 minus 7. That is 0. Yes. The answer is, yeah, they are perpendicular. So that is kind of good to know. That's it. But the cool idea is following from here. Very interesting idea, which I never thought of until, yeah, let me go to this first. I never thought of until I got to teach this class, actually. So, very cool idea. I'll show you this a little bit later. Here it is, geometric interpretation. So before I move in, actually, let me show you this idea. Let me show you the animation I found. Here is 2 vectors, okay? The 2 vectors can be perpendicular, parallel. If they're on top of each other completely, that also counts parallel. Parallelity is not necessary they never intercept. They may be just the same vector, right? They may be the same vector but different lengths. At the very beginning, that's what we have. And also the other direction, right now, they are parallel. So vectors can be parallel, perpendicular, or not. So the 3 options only. You know what's interesting? So we were always asked in school, are those 2 lines parallel or perpendicular? And there were different ways to find it using cosines and sines, blah, 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 right triangle. Have you ever asked the question yourself? Okay, so we either the answer is yes or no. That's it. It's like that's all. How about the question, but how close it is to be perpendicular? Like this is pretty close to be perpendicular right now. This is pretty far to be perpendicular. Now it's getting close to be parallel. Parallel. Now it's getting away from being parallel, getting close to be perpendicular. So if it's not 90 degrees, but it's 89, we just say no, that's it. There's like very few information about anything in 3D. So it's pretty cool that dot product and cross product answer those questions. Dot product tells you if things are perpendicular and by how much. It's kind of, actually we're going to talk about parallelity for dot products and cross products about perpendicularity. It tells you if things are parallel and if they are, by how much. One more cool representation, which is supposed to be moving, but it's not. So let's do that. Let me show you this pretty cool idea. Indeed, how much those two are parallel. So the dot product, let's write this down. The dot product measures how close two vectors are in terms of the directions. So the geometric interpretation will be how close to each other. That means how parallel. How parallel. I just put two lines together, but that means parallel. Let's do how parallel vectors to each other. How close those two forces to each other. Force and another force close to each other create a bigger force. But force and perpendicular force, they undo each other, right? So we want to know how close vectors are going to the same direction. Then it means the gravity is stronger. The heat is getting hotter because vectors go in the same direction, and so on. The wind, that's like the easiest thing to imagine. The wind is stronger if all vectors of the wind pointing more or less the same direction. They don't have to be specifically parallel, right? They can just point to the same direction. Boom, that's a tornado, basically, and so on. A strong wind. So, very cool idea how parallel things are. If they are totally parallel, then the dot product will be big. If they're completely not parallel, and what does it mean to be completely not parallel? Perpendicular, then the dot product will be 0. Exactly. So let's write down this one first. If not parallel at all, not parallel at all, dot product gives you 0. Because that means 3 lines means like definition or means, basically. Not equal, but IA or whatever. That means they're perpendicular. Dot product is 0. If they are close to be parallel, close to, and again, parallelity means close to be the same. How close to vectors in terms of directions? Close to be parallel. So almost parallel. Like the angle between them is 0.1. It's almost the same vector. 0.1 degrees, right? Then the dot product will be big. And then if the direction, big and positive, let's see. Big, let me add this. And positive. Big and positive angle. Big and positive dot product. If they are close to be parallel, but the directions are the opposite, then the dot product will be big and negative. Big and negative. So if you're doing some coding and you calculate thousands of vectors, and all of them or some of them have you calculated dot products of thousands of vectors and all the combinations of them, and all the numbers are in degrees, say 93 degrees, 92, let's say the other way around. Dot products are all close to 0. 0.1, 0, minus 0.1, 0.17. That means most of the vectors are perpendicular to each other, right? So maybe they look like so. And in 3D, imagine depths. That means the dot products give you this feeling that vectors they are very far from each other in a direction sense. They're perpendicular to each other. Vice versa, if the dot product gives you huge numbers, positive or negative, that means vectors are parallel to each other or close to each other. If dot products are positive, then vectors are like this, maybe on top of each other. Now you can claim, oh, this is a current. Water has a current. It's a dangerous place to swim. If huge but negative, then they're parallel but going different directions, and so on. That might create a swirl. So we're going to be talking about swirls actually in the months. So that's why dot product is so important. Calculation of dot product gives you lots of information without graphing it. Isn't cool? Not too bad. What do you think? Questions about this? That is pretty phenomenal. I never thought about the idea before this class, that you can ask and answer the question how parallel things are and how perpendicular they are. Have you asked the questions how circularly the circle is? The circle is perfectly circle, but ellipse is not. Ellipse, right? And how about some kind of star-looking shape. It's kind of like a circle, but it's not. So you can ask those questions. How red the color red is. How about pink color? How about whatever is between pink and red? Those things exist too. So they're pixelated definitions of those things. And so on. That's pretty important. So in mathematics, usually all of this is worked out in the matrix form, which we're going to do literally today and on Thursday. Okay, that's not new. Basically just reviewing the formula for the angle. For the angle, calculating angles, cosine of the angle between two vectors, vector times vector over lengths times lengths. That's how I remember. Vector times vectors over lengths times lengths. The only difference is, and important to remember, it should be a dot product, not any other product. Now, to show you, the top is the product of components, and then the sum of those results divided by the product of the lengths. If two vectors are perpendicular, A and B, right? Then cosine will have to have 90 degrees inside, and cosine of 90 is 0. So numerator, nu means numerator, will be 0. Now, regardless of the lengths, so this may be huge lengths, this might be small lengths, doesn't matter. The numerator gives you 0 because the top will give you 0. That's how you know. Make sense? Let's practice. Find the angle between. This is also a very nice exam problem, very classic. Find the angle between 1, 2, 3, 0, 1, minus 2. Let's do it. Try to mute your phones. Don't forget. 1, 2, 3, and 0, 1, minus 2. Okay, the first steps, right? If you stuck on the test, the step 1, know the formula. In this class, there will be lots of formulas, unfortunately. The formula tells you of cosine of angle. Cosine theta is A times B over A times B. A times B over A times B. Now you just need to remember, numerator is a dot product of vectors. Denominator is lengths times lengths, like so. So now I just need to find all of those things. A times B, lengths of A, lengths of B. Length is the magnitude. And then the picture is, if you need to know, vector A, vector B, and then theta is the angle between them, like so. So we're looking for theta. A times B. Who can calculate? Tell me what A times B is. Tell me everything. What do you have? Everything. Zero plus 2 minus 6. Amazing. Thank you. Which is minus 4. Size of A. Three squared plus 2 squared plus 1 squared. Amazing. Thank you. Square root of 14. Finally, B, I don't want to write it down again. Square root of 5. Formula. Formula gives you cosine, so maybe thus. Therefore, then. To summarize, you choose any GRE words you want to use. Just choose that. I like thus. It's fast to write. Cosine theta is A times B minus 4 divided by this. Oh, let me put it in. Divide this. You see, putting things in the square is nice, especially if you have horrible handwriting. Putting things in square makes it easy to find things in your notes. Because some formulas will need to have like 5 things to calculate. So it'll be hard to locate them later. Minus 4 divided by square root of 14 and the square root of 5. Remember, square root times square root is 1 square root. You can put things into 1 square root. So it's square root of 7t. Minus 4 and then the square root of 7t. That is a cosine of the angle. And we need the angle. And you think we're going to build a right triangle? Yeah, we're not going to do that. Just use your calculator. Theta is arc cosine, or cosine minus 1, arc cosine of minus 4 over square root of 70. And I did not even rationalize the denominator. If you don't know what it means, I did not get rid of square root of 70. Who cares? Use the calculator. Don't forget to switch to radians, degrees, blah, blah, blah. Check that. It is, I would be curious to find out the degree, because that tells me how perpendicular or parallel they are. But it's also 2.07 radians. In radians, it's a bit hard to see what is going on. 119 gives me some intuition. It is far from 90, so they're not perpendicular, blah, blah, blah. All that kind of stuff. Does that make sense? Good. So you can do that. Physical questions, ideas, suggestions. I like to slow down with problems, so make sure you understand. Or add something if you want. Physical interpretation. That's for physics and engineering majors. If F is a force and D is displacement, both are vectors, then F times D is work. F times D is work. Usually you see it in physics notes. They say W, which is work, and it's a vector because work has direction and length. Work has direction, magnitude, how strong is. Well, what I'm doing here is pushing. Somehow in my mind it's immediately pushing, which is not necessarily true. Pulling the rope, anything can be work. It's a force with which I'm pushing this chair away, right? So I'm pushing. Times is a dot product here. D, and that's direction or displacement vector. So am I displacing it this way or I'm displacing it this way? And so on. Displacement. Gives me work. How much work it took me to move the chair from one place to another place. Here it is. And the angle between F and D can be found using dot product. So that is one of the applications. Find the work done over force F, 70 newtons, and displacement D, 100 meters, given that the angle is 35 degrees. That's a problem from your homework. Maybe exam 2, we'll see. Not exam 2, maybe exam as well. Find the work done over force F. All of those are vectors, even though in the books they never write them as vectors. Technically speaking, you should understand current has direction, right? Force has direction. Displacement also. Size of displacement just tells me how far did it go. But displacement actually has direction. Maybe I'm moving it to the right, and then I change my mind and move a little bit to the left. Displacement actually, the size of displacement is only this little size. So that's important to remember. But all of those things have directions. Solution, as I told you before, the step 1 is to know the formula. If you don't know the formula, unfortunately, you're screwed. We don't give you formulas. ASU doesn't like cheat sheets, which is very upsetting. It's very this cool thing, because I've been in 2 different universities before this university, and we all allow cheat sheets. Some fixed size, but whatever you write, that doesn't matter. Some people wrote pray, for example. It was interesting to look around, doodles, examples, theorems. Here, nothing. They don't allow anything. Kind of high standards thing, which kind of very skeptical in my point of view. You don't have to be an amazing engineering with amazing memory, okay? You can just understand things, but look up formulas. Anyway, let's do it. W as a vector work is, so we are looking here, F times D. So we just learned that F times D, we're looking for the work done with the given angle. So size of F times size of D times cosine theta. That is because it came from a formula. F times D equals that. Maybe if you want, I can write it down. So F times D, that's definition of a dot product. F times D equals magnitude of F, magnitude of D times cosine angle between them. Cosine of angle between them. That gives you size of F is given force is 70 times size of D is given 100 times cosine of 35. Make sure you understand it's degrees. Switch to degrees if you did not do it before, which gives you approximately 5,734. What are the units? That's correct. Newtons times m, which are joules. Joules. I always say it wrong. Joules. Yeah. In my language, you say joule. So I always say joules. And then I try to fix myself. I don't care about units in this class. So if you ever ask this question on test, do we need to put units? The answer is no. You have lots of other classes which will take points for the units. So I'm not going to be doing that. Not my job. Yes.
Maybe I don't understand. That's supposed to be 70 times 100 or 70 times 10.
No, thank you. 100. That was a very on purpose mistake to make sure everyone pay attention. Good job. 100, yes. Lost a 0. Does that make sense? Can you do it at home? So that's the idea here. That is the idea here. So before we move on to the next topic, you don't have to write this down, this table. I'm providing it in the notes. But basically, every time we introduce a new property or a new item, I mean object, right? Vectors. We ask what can we do with those objects. So when you learn matrices, for example, A times B is not B times A. When you learn vectors, it actually has almost all convenient properties when it comes to dot product. So properties will not be the same for vectors of a dot product and cross product. If all of those vectors, then again, you don't have to copy it, but actually it's pretty fast. U times V is V times U only for dot product. You will see that. Cross product will not be like that. U times V plus W can be distributed. So it's UV plus UW. That's called distributive property. And the first one, commutative property. If there's a number C multiplied by U times V, you can multiply it separately. Then 0 times V, it gives you 0. And then 0 in this case is a vector. So 0 is a vector versus 0 is a number. In this book, which is not actually convenient, they put bold 0. That is a vector. And then not bold, that's a number. I don't like it, so I always make a notation. Do you know the difference? 0, 0, 0 versus just 0. That's the difference. One has direction and magnitude. The other one is a number. Finally, V times V gives you magnitude squared. We did this before. So those are properties of the dot product. Cross product will not be like that. That's why mathematicians always like to make this note. Oh, math is so straightforward, people say in high school. I like math because it always have very logical, makes sense. 2 times 3 is always 6. Yeah, that's not true. 2 times 3, which times? We have dot product, cross product. We have product between spaces and sets. Topological sets and topological spaces, extremely complicated, and so on. So 2 times 3, a cloud times apples. You have to also make sure that makes sense. The unit makes sense. So actually, it's more interesting than they say. More interesting than just 2 times 3 is always 6. That is not true. So we did this. Projection. One of the most interesting things and important things we're going to learn in this class is vector projection. It's the most important application of a dot product. Actually, that's partially why we learn it. It allows us to project a vector on another vector. We're basically going to be squishing. I don't like squishing. I like the idea of a shadow of one vector onto another vector. So if you zone out, before the right now. This is a good point to come back. Vector projection is a bit challenging. People get stuck with it. So let me try to explain as much as possible. Here's a picture. Vector A, no, that's vector B, 3 and 4. Remember last time I was teaching you that actually you can always check if it makes sense. This is 3, length is 4. Makes sense. So it's actually clear. Then 1 and 3 totally does not make sense. Like what? This is not 1 and this is not 3. So that is actually not smart. But whatever, it's fine. So we have A and B, 2 vectors. Here they are. What is going to be a vector projection of B onto A? The idea will be, the easiest way to explain in my mind is to show a shadow. So how much shadow does B makes on top of A? That is the idea. How much, I would say, influence of B they are on A. The closer B to A is, so if B is over here, the shadow will be huge. The farther it is, and the farther means perpendicular, right? If it's perpendicular, the shadow is just a dot, which is 0. So that projection gives us lots of information about how far and close vectors to each other. The shadow. However, the shadow is different, depends on where the sun is. That's why this explanation is a bit not professional, but I like it because it's intuitive. If the sun is on different location, the shadow will be bigger or smaller. No. We always try to make sure that the angle is perpendicular. This have to be a perpendicular angle. So if I create a perpendicular angle, what kind of shadow will I have? There are many ways of projecting B on the A, but only one that we want is the optimal one, and that's going to be called projection B. In green color, write down B and a hat. B hat, that's a projection. Another notation will be, let me actually just give you a definition first. So here it is, how beautifully it looks like. That's just basically what I draw for you, but different, but professionally. B is in green, here it is. It's called B hat. B hat, in this book you will see proj, P-R-O-J. That's not an international notation. B hat actually is more popular, as I remember. Then you always put whatever we're projecting as a big number B. Well, it's not a number, it's a vector. And this small one is projecting on top of what? It's going to be here. Projection of B onto A. Whatever bigger is projecting onto whatever is smaller. And bigger and smaller, I mean written in that notation. Because that's kind of confusing. So projecting B onto A. Or on top of A. And sometimes you will also see that there is a vector. So you also should see it's a vector. It's a vector. What kind of vector? Let's call it. So let's say the beginning was P. Let's change the color so it doesn't match. P, and then the end point, let's call it S. So it becomes PS. P and S are numbers, but PS connecting together a vector notation like this creates a vector. So projection, not just a shadow with a size, it's a shadow with direction. That's lots of information actually. So in applications, it's a very important definition. B or projection B onto A. So B hat. B hat. Let me know if you don't see. Let me zoom in. B hat, that's a definition. Or projection B onto A, I don't like there's no vectors here, is the vector projection of B on A. Vector projection. That will be the question probably even on the final exam. A multiple choice question, usually exam 1 and then final exam. We're gonna ask to find projection all the time. It has too many applications. You might be already seeing those applications, physics somewhere. It's also sometimes called orthogonal projection because it's precisely the vector it's a perpendicular vector. So it's called orthogonal, it makes sense. So This is you don't have to write it down, but it's sometimes called an orthogonal projection. You will see it in the book sometimes. Orthogonal projection, because if you take the difference between B, so the original B in blue, B minus B hat, that's green, B hat is a projection. Then these guys together are perpendicular to A. Well, that's how we build it. We build it this way. You see, I keep changing between last time there was a question about this. Why I keep changing between line, and then I make arrow and arrow. That's the same thing, just be consistent in one sentence. See, I'm actually pretty good at being consistent in one sentence. Here, I put all the lines, because if I put arrows, it'll be too messy. Here, I felt like I have enough space to put arrows, so I put arrows, but I don't put either or, I put both. So make sure if you just be consistent, either just choose one notation and stick to it, or at least in one sentence, it's better to have one notation. Usually one book should have one notation all the time. What do you think about that? You will see the formula is kind of super annoyingly hard. This is the formula. Vector projection formula. How to find B times A over A times A times A. What? Let's write this down and I will explain to you. And also my friend told me how he teaches a mnemonic funny rule to memorize this formula. Because I actually never had any mnemonic rule to memorize it. So I liked it a lot. B times A over A times A times A. That is crazy. You can always ask why they just don't cancel out. And that is a difference between numbers. Checking the time. 10:15. Good. That is difference between numbers and vectors. So you cannot just cancel out like this. Moreover, we did not even define the division of vectors. So we only know products. Let's see why this makes sense. First of all, I'm going to put lines everywhere indicating those are vectors. Now, very interesting. Dot product and dot product. So the numerator is B times A. That is a number. The dot product gives you a number. 5 minus 4. We just got minus 4 in the previous examples. A times A is also dot product. It gives you a number. So write down the whole parentheses. Inside of those parentheses, we have a number. Professionally, we call it a scalar. Number. But then a number is multiplied by a vector. Remember what is 5 times vector? It's a vector 5 times longer. So the whole answer is a vector. And I just told you that vector projection is a vector. So number times a vector gives you a vector. And this is how I usually teach it. B hat. So projection B onto A is B hat. B hat equals a number or scalar times A. How to memorize this? This is crazy. Too many A, B's, and then the order apparently might matter, might not. In this case, order doesn't matter. But this is the idea. Remember the order first. It's not always B on A. It might be A on B, C on D, so order matters here. The one that is projecting on top of another one goes first. That's how I remember it. So if we're projecting B onto A, start with writing down B. B times A. Then the one is a floor. So I imagine it a shadow, remember? B is on top of A, which is not necessarily the case, but that's how I'm imagining it, so it helps me to memorize the formula. B and A. So if I'm projecting B onto A, that will be a shadow. A shadow has a direction now. That's B hat, perpendicular. So I'm gonna do B times A over, now the size, now the A times A in the denominator. So I'm dividing by the whole length of A. That's how you can see it. A times A is A squared, blah, blah, blah. And then I multiply by A outside. This is how, very interesting, my friend, he says, it's a hugging analogy. I'm like, okay, let's see what does it mean. I was very skeptical at first, and then I really liked it. B hugs A, because B goes down to A to hug it, right? Very cute idea. So B hugs A to get BA. That is the numerator of the formula. Then A becomes so happy it hugs itself. A times A. Isn't cute? After this, I actually totally memorized the order. I just remember, don't forget outside to multiply by A. So it says, the idea is B is stuff times A. He calls it junk, I call it stuff. Stuff times A. But what is that stuff? B hugs A over A gets happy, hugs itself. That kind of makes sense. There are very different ways to memorize it. You can just memorize it as it is if you can. But you need to know this formula for 4 months at least. What do you think? I should make a contest, memorization tricks in this class, and then the best one will win, you know? Everyone have their own ways to memorize things. Hugging analogy, not too bad. Let's do it. That's going to be your homework. That's going to be a lot of stuff. Because calculating is annoying. You will be making small typos with a negative sign, get frustrated. So this will be like frustrated homework. Not at the beginning, but projection part is. But you know, it goes fast if you don't make small mistakes. And post your homework questions in the forum. I do check it. Yesterday I was helping at midnight, I think. And that's not very often. Don't rely on that. So, solution. The first step, what do you think is the first step? Use the formula. So the first step is to know the formula, right? Projection, let's color code it. B onto A. B onto A. So that means they're asking me to find projection of B. You see, not projection A. So whatever is the bigger or on top, that's the projection. Equals. And now you're like, okay, I don't remember the formula, but Julia told me if B is the projection we're looking for and B goes first, B hugs A, because that's what the idea of projection is. A gets happy, hugs itself. So dot is like a hug, basically. Dot product, if the hug is very big, so if a person is really close to me, I can make a huge hug and we hug each other. The dot product will be large if vectors are close to be parallel to each other. But if you are very far from me and you walk in a different direction, I need to like run towards you first. And so my hug will not be big at first. Did that make sense? So that's kind of how I see it. So hugging makes sense because it's exactly the idea of being close to each other or parallel. Times A outside, that makes it a vector. So make sure you remember. Times the floor where the shadow goes onto, that's A. And now you open those huge parentheses and you start calculating. B times A, you just basically multiply component by component. 1 times 3, order doesn't matter for this product. Plus 2 times 6, minus 3 times 2, 3 times 2. Well, you got it right, minus 6 basically. A times A. Just multiply 3 times 3, 6 times 6, minus 2 times minus 2. 9, 6 times 6, 36, plus 4. Too fast? Let me slow down and see your faces. And I'm going to rewrite. Always write down the vector right now, because that's going to be very important visually. Did you get any of this? Comments, critics, suggestions. People at the back, not too bad. Thank you for thumbs up. And now what do? You calculate this number and multiply each component by this number. Because I'm extremely smart, I can see right away. It's 9 over 49. Well, I have it in my notes. 9 over 49 times 3, 6 minus 2. And now you multiply component by component. 3 times 9, 27, blah, blah, blah. That is not very interesting. 49. Remember, the answer better be a vector. So in multiple choice, bless you, I will give you 2. It's always there. I can actually show you that problem on the exam right now because we already have practice exams, an example of the exams on the website. So this problem is there with different numbers, right? We just change numbers. And the thing is, we give you 5 different answers, A, B, C, D, E, right? But E is none of the above. 4 of them, 3 out of 4 will be vectors. 1 answer will be a number. What number? Plus, minus, and it's some kind of number like 119 over 49. I don't know what it is. So your job is to remember it's not a number, it's a vector. So some people will choose a number because they got confused. That's the way to check. That's good, yes. After this, they ask us to find scalar projections. Scalar projection is basically a size of the projection. It has a different formula, unfortunately, and a different notation. But the idea is, intuitively, the scalar projection is defined to be the length of the projection. So projection is a vector, right? It has length and direction. But what if we just want to see how big the shadow is? No direction needed. Then they code comp, also not international notation. C-O-M-P, comp B onto A, B onto A. So instead of having direction, we don't have no direction, just a size, basically. And the formula is weird. Let me wait for you to draw this picture. The formula is, let me know if you want me to go back. Here it is. I can go back in a second. Let's just put the formula in. This is the one that's hard to memorize. So I give it on the quiz and see if people remember it, and if not, I don't give it on the exam. But I'm not the one who creates exams. The coordinator does. So we'll see what she will create. So comp is A times B over size of A. It comes from the right triangle, SOHCAHTOA. Nobody knows SOHCAHTOA outside of America for you to know. So people just actually remember how SOHCAHTOA works. But I never knew it. I just know how you guys use it, but whatever. In the FOIL, nobody knows what FOIL either. It's called distribution, okay? FOIL. Only Americans created this FOIL, and now they teach. Let's do FOIL. International students in the room have no idea what people are talking about. What does that FOIL thing mean? So I teach people how to teach diverse classes, which has ESL students, English as a second language. We have many of them, right? Hispanic students and many other Native American students and international students. So don't use a FOIL without explaining what the heck FOIL is. What is SOHCAHTOA? I don't want to explain, so I'm not going to use it. That just makes sense. Basically, it's the length of that projection. Check it out. This one is projecting A on top of B. So A times B over B size if it's A onto B or vice versa. That's a new formula now. And do you need me to go back? Yeah, which one? This one? Yeah, I felt that. That's good. So we'll ask you to find that as well, using a new formula or not. The projection, I will just let you know the application so you feel a bit more motivated. The projection allows us to decompose vectors in a way very special, especially useful in physics. And with decomposing, and we're using different vectors, using displacement and perpendicular vectors. That is a really, really helpful in physics with gravity multiplied by the force of the rocket going away from the floor. So the rocket going away from the floor is perpendicular, gravity pulling it down, the projection of the angle is going down. It represents lots of things. So projection is derived from the dot product. So dot product is important, projection is important, and size of the projection, which is called comp, is also important. Finally, you don't have to write this down. Let me just show you. As you can see, I mentioned two notation verbally. B onto A or B on A. I think both are correct. I've seen both. A vector called a vector projection. Vector projection. There are other projections existing in the world, so this one is a vector onto vector. It's projection B onto A, if it's B onto A. The scalar projection is comp. basically it's a length of that projection. If I don't care about the vector, I just want to have a scalar. And here's interesting, if it's less than 90 degrees, then it's positive. And it's negative if it's not the case. That makes sense, because when I was teaching this for the first time, I was thinking, wait, so we keep showing this classical example. When one vector, say u, goes on top of v, yes, I can see the shadow. The shadow will be this, right? So projection, shadow going down. But what if u is looking completely different direction over here? What's going to be the projection then? The projection will be here. It will be still a shadow. And the answer will be negative, indicating that the angle is open more than 90 degrees. So it's still called a projection because vector is infinite, right? Vector is going this direction. But we're imagining that it has a tail and projection goes down on this invisible part of it. Yes?
So I'm confused on which one is the formula out of the things you showed. There's things with like...
Good question. Yeah, let me go back. The question is which formulas actually are formulas and which are just notations. Yes. Let me finish this and I will go. Oh, actually, I think I will go right now and mention that. Very good point. Thank you for saying that, because we will have lots of weird stuff. And then I try to make clear which formulas you need to know. I highly recommend you to start this week having a paper, a huge one, and start writing down all the formulas we're learning. We already have like 5 formulas from the beginning. We already have dot product, projection, size of the projection, which is comp. Last time we learned vectors, cosine, angle between vectors. Now we have angle between vectors using dot product. So we're gonna have all formulas will accumulate so fast that your brain will be burning, unfortunately. There's just so many. So very smart that you're asked to know which one we need to know. Before I move on, do you see my point here? Like what is happening when the vector is away, looking away from v? That has connection with dot product. If it's far from v, the dot product will be small, blah, blah, blah. So from dot product, we find the projection. Projection gives you a negative number if theta is larger than 90 degrees. So for these, remember 2 formulas. Good question. Remember vector projection, b hugs a over a hugs a times a. Remember that. Put it in the box. Remember the formula of the size of the projection. This one. Comp b over a. Again, b goes on top of a, onto a. B projecting onto a. That's basically a size of the projection. So a times b, let me change the color. A times b, both are vectors, over a magnitude. Remember that. And cosine is involved from the very beginning of the definition. So that's also is important. Remember, I guess 1 is just good enough. Another one comes from this one. Comp. The projection of b onto a is size of b times cosine. And then from here, you can always go back to the cosine. If they ask you to find angle between vectors, you can use projection to find it. But people usually don't do that. Good question. Many other questions? All questions are very welcomed. Yes?
Yes, so it'd probably be more work to do this, but say you had the projection vector, like you found it. Could you find the magnitude of that?
That's what I would do, yes. They just try to skip that step. The question is, why do we have to have one more formula if they already told you it's just the lengths, right? It's just the length of the projection. Yeah, to have both. To avoid to find the projection and then the length of it. The answer should be the same, you should check. And it should be a number, right? So, of course, the examples, I don't want to go to that example. You will have lots of them in your homework anyways. But what I want to show you in 10 minutes is this component breakdown. Let's see, where is it? I just saw it. Oh, the force and displacement at the very end. So vector, blah, blah, blah. This is very interesting from physics point of view, basically. Application of projection. That's the last thing to know today. The projections allow us to decompose vectors. And that's you don't have to write this down. What you should write down is this. I think this is good. If B is force, why it's not F anymore? Why it's B? Whatever. And A is displacement. Why it's not D? Okay, fine. That's physics books and chemistry books are so hard for me because they sometimes switch between notations and it's not convenient. Most people try to stick to one notation. Then B hat, that's a projection, remember? Projection. So that is, let me write down since it's a new term for you. Projection of B onto A. B hat, that's what it is. It's called tangential component of the force B along A. So you will see that in physics book. People who don't take physics classes like, I'm not going to see the physics book ever in my life. So why do I need that? It has lots of application in math too. But because it's a calculus 3 for engineers, you were supposed to take 270 whatever, I forgot. That's calculus 3 for not engineers. Then you would not even probably see that. But here we push engineering stuff. Do you know why? Because engineering department math department told us to push engineering stuff. So if you hate that, you know whom to blame. B minus B hat. That's the difference between original B and the projection of B. That is called normal component of the force perpendicular to A. Let's see it on the graph. Let me draw it from scratch. Oh, here it is actually. Here it is. So a force is B, can be broken down in two different components, and maybe more than two. And that's one of the applications of the projection. We can decompose vectors. Decompose means writing down as components. If B is the force, how strong I am pulling towards myself the chair. And then displacement is A here. Then the projection will be B hat. That's the shadow, right? Then we're going to have this idea. Just B hat is a tangential component of the force, while the triangle part, this one, B minus B hat, it has direction up. That is called a normal component. Normal means perpendicular. So why that is important? Because we're rewriting the force as a sum of tangential and normal components. And now we can see how small, again, remember, this is what I think is personally interesting. If B force was very perpendicular means almost perpendicular, right? So close to be perpendicular, then the projection will be tiny, right? So the small B hat called small tangential component shows you how the correlation between A and B are. So this is B and this is A, right? And then this component will be huge. B minus B hat, which is called normal component. That will be large. Versus one more example. What if A is over here and B is over here? And they're almost the same. They're almost parallel. So the number for the dot product will be huge. Then the projection will be very large. This is the projection. B hat will be big, so tangential component will be big. And this perpendicular piece, which is also a vector, by the way, will be tiny in its length. Then both of these give you information how vectors behave towards each other. So force being close displacement means, we're moving the chair far and so on. Force and the gravity. Is it close to gravity? Am I pushing gravity towards the planet? Am I actually pushing something towards the planet? So I'm adding those two forces. Or pulling it away. If I'm pulling it away, then the forces are perpendicular in displacement. The forces are perpendicular, then the projection will be tiny or zero, and so on. So all of these have lots of applications in physics and engineering, and so on. Always imagine also the bridge, civil engineering building bridges and third floors and connectors between floors. All of those have forces and they have lots of projections there, lots of calculus involved. To be honest, I talked to several architects, professors who are retired. Somehow my neighborhood has like 5 people from ASU are retired professors. And 2 of them are architects and engineers. And they do this. They used to do this every time. Double integral, triple integral, which we're going to learn in this class, and that. To know how forces collapse together or not. Will the bridge collapse? Or it will be keep holding by 2 floors and it'll be safe. Good job, people. Let me know if you have questions. I'm walking you right now towards office hours or study sessions, so you can just stay and walk with me.